Okay, 6B, who wants to read it? Emily, thanks for volunteering.
How did you get down Leo?
Because I just noticed in the camera you could see like this beautiful chemistry, and then couldn't see the Y. So I thought, maybe somebody watching the YouTube video wants it. Shout out. 6B.
Systems at equilibrium are responsive to external perturbations, with the response leading to a change in the composition of the system.
Okay, so we talked about what equilibrium is. We talked about how to calculate what the concentrations of things are going to be at equilibrium using an ICE table and using the K value. Now we're going to talk about if we have a system that is at equilibrium and we do something to it. We stress it in some way. We perturb the system. Right? Perturbations are little stresses, right? Little disturbances. If we do something to a system that is already at equilibrium, we have to understand how the system is going to respond. So, did we look at this simulation? Yeah. Okay. So, dump a bunch of A in there. Close the line so you can actually see it. Is the system at equilibrium?
No.
How do you know?
Because there's more green particles turning red than red particles turning green.
What?
There's more green particles turning red than red particles turning green.
Okay, so the rate of green particles turning to red is not equal to the rate of red particles turning to green. You can also take a look at the numbers on the bottom, and if those numbers are changing over time, which this thing is going down, it was 176, now it's 169, okay. We're not at equilibrium. At equilibrium, this number should be roughly constant. All macroscopic values should be pretty much constant.
No.
Now we're way down to 145. Again, if we were to graph this,
I think that's at equilibrium.
we started out with 300. Now we're at like about 129, 130. That's the number of greens. Okay, the number of reds have gone up. Now we're down to like 120. So again, this simulation is a little imperfect because there's only so many particles there. There's also a physical, it has to get from one side to the other. That's a little bit of an issue. But I would say we're hovering between about 120 and 125 here. So I would guess we're probably about at equilibrium. Let's call this 125, and then we'll call the reds like 175. So what's the equilibrium constant for this reaction? Products over reactants. So 175 over 125. Get out the calculator.
I thought I had to do concentration.
What?
I thought I had to do concentration.
It is supposed to be concentrations. We don't have a volume on this thing, so we can't really do that. We could just do it with particles in this case. What? 1.4. Okay? Now, of course, it's gone down a little bit.
Is there time limit?
No, it's just going to keep going. Okay. So, we're probably close. 1.4 is probably a decent estimate of the equilibrium constant. Now it's back up to 125. It was down to 115. All right. I'm okay with this. All right. So, what are the ways that we can perturb this system?
Add heat.
I'm going to save that one for a minute because that's a hard one to actually understand what it's going to do. The easiest type of perturbation we can do to a system that's already at equilibrium,
Add more pressure.
add more of something. Okay? So if we think about the cork war, if I'd have chucked a bunch of extra corks in on one side, what would have happened? Okay? I can do that in this simulation. I can pause it. Maybe I'll I'll wait till we get up to our equilibrium, closer to our equilibrium numbers. Come on now.
Okay.
Of course, it's going down. Well, maybe our equilibrium constant's off.
Are we talking 190 over 110?
Yeah, how about 190 over 110? It seems.
1.72.
Actually, I would say it's gone up a lot, it's gone down a lot. I would maybe do 185 over 115.
1.61.
Okay. So, what would happen if I were to dump 100 extra in on this side?
It went down, so.
What do you mean it went down?
So the new balance on each side of the equilibrium is still 1.6.
Okay, we would have to do something to get us back to 1.61. Okay, so if this reaction is A turns into B, and it's reversible, we could say that if I dump 100 extra in, so we had 114 over on this side, I want to make it 214. There they go. Put a bunch of extras in there. So if we have 214 on the A side now, and should have been 215, and this should have been still 185, this represents a new set of conditions for this system. Is it at equilibrium?
Not right.
How do we know?
Because
Because the ratio is not 1.6.
The ratio is not 1.61. What is the ratio?
less than 1.
It's greater than
0.8.
What is it?
0.8 something.
0.86. It's a weird looking 8, but that is an 8. Okay. So again, anytime we want to know whether the system's at equilibrium, we calculate Q. And for this new set of conditions, Q is 0.86. Q is not equal to K, so we are not at equilibrium. What we now have to ask ourselves is, how will the system respond to get us back to equilibrium? Our Q is too small. Agreed?
Yes.
What does that mean?
We need to add, or
there's going to be more products formed.
More products.
We need to make more products, because that's our numerator, right? And we have to get rid of our reactants. That's our denominator. We need to make the top bigger and the bottom smaller, right?
Yes.
So we need to make more products, and we need to get rid of our reactants, okay? So we sort of already talked about this, I think, when we were doing the ice table, right? This is something you should be doing every time when you plug in initial values into an ice table. Calculate your Q, think about which thing needs to go up and which thing needs to go down to get us to equilibrium. All right? This is just another example of that. If I add a bunch more reactants, Q will go below our K. The system needs to shift to form more products to get us back to a equilibrium ratio of products to reactants. Okay, so if I let this thing go, you can already see we're down to like 205 here. 199, okay? So we're definitely getting rid of reactants and forming the products, okay? What will the equilibrium concentrations or equilibrium amounts be?
215 minus X.
215 minus X here, 185 plus X here. And now we can plug into our equilibrium constant expression. K equals the ratio of products to reactants, 1.61. Has to equal 185 plus X over 215 minus X.
61.7. But can you have a decimal for the final answer?
In this, no, because we're representing numbers of particles, but yeah, if you're calculating it, it's okay to have the decimal.
So like for the AP test, we ever have to do this in the free response?
Well, you're going to be doing molarities,
Okay.
so yeah, you definitely want to worry about sig figs, but definitely going to have decimals when you're doing concentrations. Okay? Anybody else get 61.7?
I did.
Emily did? Can I get a third?
Yes, I did, yes.
You're graphing it?
Yes, and it's loaded.
Take your time.
It's taking her so long.
So long, I could have solved this algebraically.
Okay. So if x is 61.7, how many a's should we end up with when we reestablish equilibrium?
153.3.
153.3. And this we should end up
246, 47.
Is there a label for the row where you write the real answer once you calculate x?
No, I mean,
Do you just write it somewhere?
yeah, I mean, we're basically just plugging our x back into
Yeah.
the equilibrium row, so I would just write, you know, concentration of A, even though these aren't concentrations, I would just make that somewhere else on my paper. Just show that I plugged back into the equilibrium row, and here's the number that.
Would you have to just say?
Ho, ho, ho!
That was loud. Would you have to just say 153 because sig figs?
Yeah! It's hovering right around 153. Yeah, I mean, in this example, sig figs are a little bit weird. We also have actual particles, which we can't split up and have 0.3 of a particle. But yes,
That is fun.
isn't that amazing?
Yeah, it is.
It was at equilibrium before I even came back and looked at it. But yes, eventually we'll reestablish reestablish equilibrium, in this case by shifting the system from the left to the right. Okay? Now in these types of problems, Le Chatelier type problems, they're going to ask you, if I do this, which way will the system shift? We just determined that if we add reactants, the system will need to shift to the right to form more products. It's trying to relieve that stress. We just stress the system by putting a bunch of extra stuff in the reactants. The only way for the system to respond is to get rid of those extra reactants, turn them into products to reestablish equilibrium. Okay? So on a test, they're going to ask you, does it shift left or does it shift right? In this case, it shifted right, towards the products. Why? Because when we added all those reactants in, our reaction quotient was no longer equal to our equilibrium constant. Because it was too low, we need to form more products and get rid of our reactants to reestablish equilibrium. Okay? And now we've got this situation where we're back to our equilibrium ratio. Okay? What would have happened if I dumped a bunch of extra B's in there? The system would shift to A to get rid of those extra B's. Right? If I put extra B's in there, my reaction quotient is going to be higher than K. If the reaction quotient is higher than K, we got to get rid of products and make more reactants. So it's going to shift to the left. Okay? The other thing that's important to keep in mind, we said the system was shifting to the right. Okay? But originally there was only 135 A's in there, right? Before I stressed the system and added, or sorry, I guess it was 115. Before I added 100 more. Okay? So even though it's shifting to the right, both of the amounts are increasing. That's an important point to keep in mind. We are actually increasing the concentration of both of these things. We have to be because we're dumping more stuff in there. Okay? But when they ask about the shift, they're saying, how does the system get back to an equilibrium ratio? Okay? So compared to what we had when the system was not at equilibrium, the A went down. Okay? Compared to what it was at the original equilibrium state, it went up. But to get back to equilibrium once we perturbed it, we had to get rid of some of that extra reactant. Does that make sense? I don't know, in my head it just sounded like I was reading one of your free response answers.
Yes.
You just keep saying things, and you have some of the words you need, but it's not. Does that make sense?
If you write all the words enough times, it's good enough.
True. A million monkeys on a million typewriters. Okay, what would happen if I take some stuff out of a system that is at equilibrium?
Still balance out.
So let's say, of course, now we're not at the. Every time I want it to be at the equilibrium ratio, it's not.
Just gotta give it some time.
Get over there, you punks. Keep going. Yeah, kick him back over there. All right, close enough. 151 and 249. That was pretty close, right? What if I take some stuff out? What if I were to remove, say, 100 from the B side? So that instead of there being 249, what if now there's only 149?
So
It'll
reactants
shift
would
left.
react.
It'll shift right again.
It will shift right. Why?
Because
Yeah,
if you
yeah.
calculated,
Because the K value is gonna be,
It's a negative, or not negative.
if you
underline.
calculated
If I get rid of B's, is my Q value, my new Q value, less than K or more than K?
less than,
Less than K, right? And we know if we're less than K, we need more products, we're going to have to shift to the right. You can also think of the fact that if I pulled a bunch of these away, the system's like, hey man, I'm not at equilibrium anymore. It's going to try to relieve that stress. We pulled away a bunch of B, the system's going to shift to replace that missing B. Just like when we added a bunch of A, the system said, let's get rid of some of that extra A by shifting to the right. Okay? So there's sort of a qualitative way of thinking about how the system is going to shift and why, and there's definitely a more quantitative way using Q's and K's. This is the way I like better. Okay, because it's a more complete understanding of why the system does that thing than just being like, no, it doesn't like all those extra A's in there, so... Yeah. And what will I write?
100%.
0.
What will my comment be, my snarky comment?
Good job.
I'm proud of you, I taught you well.
These chemicals do not have nervous systems. They don't want anything.
They want more electrons.
They want more electrons. Okay? So I think the easiest thing to understand is when we take away or add something, right? Now I can, I could do a little example for you. Where's my dog? Crap. Okay. What?
is there a reason you scream?
The reason I screamed? Did I scream?
Really? No!
No! Well, I had this all prepared, and then I stole some of the chemical I was going to use for my Chem 12 lab. Okay, so I'm putting a little water in here,
What's the thing on the bottom?
and I'm going to add something called universal indicator. Universal indicator is actually a weak acid. It's actually a mixture of weak acids. Okay? But this indicator, oh, they're learning about it in Marcella's class.
Your handwriting is better than his.
The indicators that are in here are themselves weak acids and weak bases. Okay? So, I probably shouldn't have used universal. Well, here's the thing. It'll work, I guess, for what I'm trying to do. I'm going to add some acid to this, some HCl. And it turns pink.
Red.
Turns red. Okay. What's happening is that we have some indicators in there that are themselves weak acids, right? So they've got some hydrogen on there, some other anion that holds on to that hydrogen pretty well, which is why it's weak acid. It doesn't like to donate. It doesn't very often donate that proton to water, but it can, and when it does, it creates H3O+, and whatever that anion is, the conjugate
Base.
The base.
Conjugate base of this weak acid, right? So if we go in this direction, this thing is going to accept a proton from H3O+, so that makes it a base. Okay? Now, I added HCl to this. HCl is a strong acid, which means basically there is no HCl in this at all. It's actually all H3O+ and Cl-. So actually what I did was I took a system that was green, I added this, and it turned red. So if we think about acid-base indicators, have two different colors. One color when they have the proton attached, another color when the proton is not attached. If I added a bunch of this, which way did the system shift?
Left.
When I add products, the system has to shift to the left to reestablish equilibrium. And we're seeing now if I shifted it to the left, this form must be the sort of reddish version. Okay, now I'm going to add some sodium hydroxide, NaOH.
What?
And we saw it turn purple. Well, where's NaOH in here?
It's the OH minus.
So it's like,
No.
NaOH is not in here, agreed? OH minus is not in here, agreed? So I'm not actually adding anything that's in this equilibrium. Why did it shift? When I add NaOH, the OH minus will actually react with this, taking it away. So it's just like in the simulation where I just dropped the number of products. When I added the NaOH, it got rid of some of this. If I get rid of this, the system has to shift
Right.
to the right to replace those missing H3O pluses. Okay? So that shift to the right, we saw this color, then the purple represents the conjugate base form of this indicator.
Can you get it back to green?
If I'm good. But yeah, you can, I can add it slowly and it turns sort of pink at the top, that's cool, and then once it mixes together, now it's back.
Oh,
Now,
you know, even it up.
I'm gonna try. It is very, very hard to get the exact stoichiometric mixture in there that's going to get us back to green. Whoa. Okay? So that's an example of what we mean by adding something or taking something away. It's impossible to shrink yourself down and start gobbling up product molecules and absconding with them, right?
Yes.
So when we talk about removing something, we're removing it with another chemical reaction. Okay, so we could react it with some other molecule that produces something that's no longer part of the equilibrium that has the same effect of removing that thing from the system. Right? I added NaOH, it's not adding anything to the system, but it's reacting with this, pulling it away, which then causes the system to shift to the right. Cool?
Kind of get it.
Kind of get it. Okay, well we're going to do a Le Chatelier lab. So hopefully by the time we do that, then you'll really be able to think about this and it will all make sense.
Yeah.
Okay?
what is,
How short are they?
which one is like just like, if you add or subtract anything, it doesn't count, right?
I'm sorry? Le Chatelier is saying when we stress a system that's already at equilibrium. This thing was green, it was already at equilibrium, and then I stressed it. I added a bunch of extra stuff in there. So Le Chatelier is saying, how can we predict which way the system is going to respond to get us back to equilibrium? All right?
Is that all 6B?
No! That's the easy part of 6B.
What?
The easy part of 6b is to think about, well, if I dump extra stuff in or if I take stuff out, I can really easily think about what that's going to do to Q, and then what I need to do to get us back to K. All right. A slightly harder. Actually, there's two other ones. I'll go maybe the medium hardness, medium difficulty.
You do the hard one, then
We'll do the medium difficulty. The next stress that we can apply is to dilute a system. Okay, so if I have this system here and I add water, what will happen? Both the concentration of the reactants and the concentration of the products will go down. So let's say we had, now this is sort of weird because the universal indicator actually contains multiple indicators, which is why it's green in the middle. There's no way you can mix red and purple and make green. There's some other indicator that's making it green sort of in the middle. Okay? But let's say we started with this indicator and it was green. Well, let's make it just really slightly pink. That's light bulb.
Why do you add a little bit more water?
Maybe you like put
So-
everything that had diet.
Well, yeah, that too, and I just put way too much in there. Okay, but let's say that at equilibrium, let's just make up some numbers. Let's say at equilibrium, when we get this sort of greenish thing, or maybe it's very slightly pink, let's say that the system is 1 molar here. Well, let's make it 1.1 molar. Just a very slightly larger amount of the red one than the purple one. Okay. Let's say this is 1 molar and this is 1 molar as well. These are not the actual concentrations for this particular indicator. Okay. But this is just to illustrate the point here. If this represented an equilibrium system, what is the value of K? Well, for this reaction, when we calculate K, it's, remember, the concentration of the products over the concentration of the reactants. The products in this case are H3O+. Raise it to the 1 because there's a 1 in front of it. A minus to the 1 over concentration of HA. Right? Remember, we ignore H2O in our calculations because its concentration doesn't really change when we do these chemical reactions. Okay, so if this represented a system at equilibrium, then we would have 1 molar times 1 molar over 1.1 molar. Our K value would be
0.91.
0.91. If I dilute this system, what will happen? All the concentrations will go down, right?
So K stays the same.
Let's say we double the volume. If we double the volume, what will be the new molarities?
0.55.
This would be 0.55 molar. This would be 0.5 molar. And this would be 0.5 molar. Are we at equilibrium? Only way to know is to calculate Q. Q looks just like K, right? It's still products over reactants. It's just not necessarily at equilibrium. So 0.5 molar times 0.5 molar over 0.55 molar is what? What is it? Woo! Are we at equilibrium?
No.
No. would that be?
Science.
We diluted everything. Why would it shift? Why would we have our Q not equal to K?
Molds.
They went down by different amounts.
Not just that, but because we have two things in our products and only one thing in our reactant, it's cutting all these values in half is going to affect the numerator more than it affects the denominator, right? So for this system, we diluted it and Q went down. How do systems with Q less than K get back to equilibrium?
Shift to the right.
Shift to the right. We've got to increase our amount of products and decrease our reactants to get back to equilibrium. So when we diluted it, it shifted to the right. Okay. Let's say we have another theoretical reaction. I'll just do this one in the gas phase. And let's say, similarly, we have at equilibrium 1.1 atm as the partial pressure of A2. Sorry, I'm going to make this 1 atm. As the partial pressure of A2, 1 atm as the partial pressure of B2, and 1.1 atm as the partial pressure of A2B2. I don't think we've done any equilibrium constants in the gas phase yet, but it ends up being pretty similar to when you do solutions. It's just, instead of concentrations, we're going to use partial pressures. So K for this reaction will be the partial pressure of the products, A2B2, over the partial pressure of the reactants. And we're going to raise these to any coefficients, which we don't have any coefficients for this reaction, so we're good. Are you ready for step 2? Too bad.
That's the
Neither
right
am I,
answer.
'cause I don't know where I put it. Right where I left it. Okay, what is K for this reaction? 1.1? Transky.
What?
1.1 ATM over 1 ATM times 1 ATM. Yes, our K is 1.1. Okay, now, no, it does not have units. I mean, technically, the ATMs don't cancel, but normally we just make it unitless. So, now, let's say we double the volume of this. Okay, so when we're in the aqueous phase, we would add water to dilute something. If we're in the gas phase, we just expand the container that we're in, and that changes the volume. What would happen if I double the volume of this system?
2.1 over 2. Over 4.
P1V1 equals P2V2. If I double the volume, what will happen to these pressures?
They'll go down
By how much?
by
We'll get cut in half, right? So this will go down to 0.5 atmospheres, this will go down to 0.5 atmospheres, and this will go down to 0.55 atmospheres, right? Initially. Then we're going to ask ourselves, okay, we doubled our volume, now we've got some new pressures. Are we at equilibrium? What's the value of Q? 2.2. So now Q is greater than K. When Q is greater than K, what happens?
Shifts left.
we shift to the left to reestablish equilibrium, okay? Well, wait a minute. I doubled the volume here and it shifted right. I doubled the volume here and it shifted left.
Products.
So whichever one has more things.
When we change the volume of a system that has different amounts of moles of species on the two sides, if we give it more space, it's actually going to shift to the side with more moles. So we shifted right in this case because we had more particles on the right side. In this case, we shifted to the left because we have more particles on the left side. Okay? If I were to decrease the volume, so if I crush down some equilibrium gas phase reaction, or if I maybe evaporate the water out of an aqueous solution, if I decrease the volume, how is the system going to shift? The opposite. It's going to shift to the side with less moles. Okay? So again, that's another stress that we can do, change in volume for a gas or diluting an aqueous reaction. I never actually diluted this. That's because I'm not all that confident that it's going to shift. I think I'm too far from equilibrium to actually see anything happen.
Why is it yellow?
Maybe towards the top. It's yellow because it's like on its way to getting back towards the green, which was right in the middle, and then eventually towards the purple, right? So yes, when I diluted it, it actually did shift to the right. I know it doesn't look like that because it's not turning purple. That's because this is multiple indicators in one. This is a great example to use. You're going to do some examples in the lab on Monday where you're actually going to use some just single indicators in there, and you'll do these same types of things, okay? But yes, it definitely is not pink anymore, which means there is a shift, and I assure you it is shifting to the right as we predicted. Emily?
Is the increase in volume means it shifts to the side with more moles, decrease in volume shifts to the side with less moles? Can
Yes.
you sub in molarity for volume? Is it the same concept?
What do you mean
Like
sub-molarity?
say instead of increasing volume shifts to the side with more moles, increasing molarity shifts to the side with more moles?
No, increasing molarity shifts to the side that doesn't have that substance in it. We already talked about adding or removing something.
Why is increasing molarity adding or removing something?
I mean,
with
you're
the
affecting the
problems here with
concentrations through the
aqueous
volume.
things.
You can't say increasing the concentrations. I'm not sure what you're going with. You're
Are-
still talking about changing the volume?
I'm trying to make a parallel between what changes in the volume does and what changes in molarity does. I understand. So maybe it's hard to increase molarity for things because you can't unless.
Well, if we dilute something, like I did here,
Yeah.
the molarities decrease, right?
Yeah.
And the molarities decrease if there's not the same number of particles on each side, then either the reactants or the products is actually going to decrease by more,
Okay.
right? So when we did this system in equilibrium and we diluted it, because there was two products and only one reactant, the products numerator value went down more than the denominator did, right? Okay, so if we're affecting the products more than we're affecting the reactants, then we need to replace some of those products. We're going to shift to the right. We're going to shift to the side who had a bigger overall decrease in molarity, I guess is what I'm trying, if I'm understanding what you're trying to do.
I just you cleaned up the volume one super nicely, and we're if you increase volume, the reaction will shift to the side that has more moles.
The
of
reason
them.
is, the reason I'm trying to explain,
Yeah.
is not because it wants to be more moles, it's because when I increase the volume,
The dilution affects. The
I
more
decrease
moles
all concentrations or decrease all partial pressures, right? And so if there's more particles on the product side, then the numerator is going to decrease more than the denominator. If there's more particles on the reactant side, then the denominator is going to decrease by more than the numerator. Okay? So in this example, Q is going to go up compared to K. In this example, Q is going to go down compared to K. Does that make sense?
Yeah. So
So really, it
It's
is
just- it's
affecting Q. That's what I really want you to think about. I don't want you to try to memorize, oh, it shifts to the side with more moles. That's what you do in first year chemistry.
I was just trying to relate the volume with the molarity. And my mistake was that I was saying increase in molarity, but an increase in volume is the same as a decrease in molarity.
Exactly. Okay, good. All right, ready for the hard stuff? Temperature. Temperature. How does changing the temperature affect a system that has already achieved equilibrium? Well, let's look at a system that is at equilibrium.
Would it have changed their slope or like their speed?
It would change the what?
Their slope or like their speed?
What slope?
Like, you know on the graph?
What graph? I know about lots of graphs.
The,
Maxwell Boltzmann,
not that graph.
the equilibrium.
Equilibrium graph,
Yeah,
yeah, and how like it stays out.
yeah.
Because they're going at like a constant, or they're changing at a constant. Like if you increase the temperature, won't you be changing it like a different?
But the slope at equilibrium is 0.
So wouldn't that slope change?
Can the rate change?
Yes, the rates change. Somebody thinking about kinetics. When we change the temperature, we change the rate. But the question is, if this system is at equilibrium, we're going back to,
Wait, so it's already at equilibrium?
yes,
and we're-
all these Le Chatelier things, we are saying the system is already at equilibrium. Now we are doing something to it, okay? So let's say we are at equilibrium here. This is the same reaction we were talking about before. B over A is, what did we say it was? 185 over 115? What was that? I forgot the number. 1.61? Okay. If I increase the temperature of this system, what will happen? Well, am I adding more A or more B?
No.
No. Am I changing the volume? No. So is Q changing?
Maybe.
No. What are we really doing? It comes back to what Andy said. Maxwell Boltzmann. Okay, so I made a really awesome Excel spreadsheet. Actually, somebody made a really awesome Maxwell Boltzmann spreadsheet, and I modified the heck out of it to show you what I'm trying to explain here. Okay, what does increasing the temperature or decreasing the temperature do to this system? The best way to think about it is to think about Maxwell Boltzmann. Okay, so what this simulation does is I can put in temperatures for the reactants and products. That's going to determine the shape of the Maxwell distribution, right? I can plug in activation energies for the forward reaction and for the reverse. So right now our reaction profile looks like we got an endothermic reaction. But the simulation we were just looking at was exothermic. So I want to switch it just so it's more like what we just talked about. Okay, so now the reaction profile looks kind of like that simulation, right?
Oh, that's cool.
Okay, now what changed on my graph? Did anybody notice?
Oh,
The
okay.
shaded.
The shaded area. So what does the shaded area represent?
I feel like the amount of particles that actually have the reaction. They have, like, natural
Yes,
reaction.
if we look at my legend here, the light one are the reactants, the dark ones are the reactants which can react. So here's my activation energy right here. I actually calculated based on this activation energy what speed the particles need to have, what speed they need to hit with to cause this reaction. So it turns out for the forward reaction it's 137 meters per second. So any particle with at least that speed could react. Of course we know it's got to have the right orientation and all that stuff too, okay? But of all the particles we have, there's a pretty big fraction that can turn into products, okay? This is just like when I started out the simulation and I dumped 300 particles in on the left side. Okay? Not all of these particles have enough energy to get over this bump, right? Most of them do because it's a pretty small bump, okay? But the dark red fraction tells us how many can actually turn into products. Okay, so then what I can do is I can play with the numbers here. All right, so this is sort of like we were looking at some data before. So let's say the reactance goes down. Well, the reactants are going to turn into products. So in blue here, now we can start to see a Maxwell distribution that represents my products. My products need to get over this bump to turn back into reactants. That's a larger activation energy. So if you can see down here, maybe you can't right now because there's so few products, but I'll start to change this even more. And as the reactants get converted to products, we start to see this distribution. Stop dropping stuff, man.
Get into this.
Okay. Oh man, I almost fell out of my seat. That was so exciting. The products in blue, we're starting to get more and more, so that's why the mountain is sort of building up here. But you can see the shaded area in blue is different. Notice the shaded area in blue. Can you guys see that back there, Emily?
Sort of.
The blue actually doesn't start being shaded until about here. Because the reverse activation energy is so much higher, we need a higher speed for the products to turn back into reactants. Okay, so when we look at the shaded area for blue, there's a lot fewer products that can turn into reactants than there are reactants that can turn into products. So on the upper right here, I've actually calculated there's 1,200 reactants right now that can turn to products of these 1,700. And there's only 100 products that can turn back to reactants. Are we at equilibrium? No. If we had 1,200 quarks flying in one direction and only 100 flying in the other direction, there's going to be an overall change in the amounts, right?
Is the medium blue color, and just because the graphs are is just
Because they're overlapping.
Okay.
Yeah. So yeah, that's kind of confusing. This first darkening is actually the darkening of the red behind this. I
Okay.
don't know if there's a way that I can fix that.
You can make it less transparent.
Okay. Somehow.
I think you just have it all the same color, just some of it's more transparent, so you have to like change the color of it maybe.
Yeah. All right, I'm not going to do that right now, but I could. Okay. So I'm going to keep getting rid of reactants. They're going to keep going down until the area that's shaded for red is the same as the area shaded for blue, right? And again, we can see the amounts on the upper right here. We still have more reactants that can turn into products than we have products that can turn into reactants. Okay? So we're going to keep going down, keep going down. Now again, equilibrium doesn't mean equal amounts, right? Right now I have equal amounts of reactants and products, but because of the different activation energies, way more reactants can turn into products than products can turn into reactants. All right. So, in general, for exothermic reactions, you're going to need more products than reactants to be at equilibrium. Okay, let's see. 700 is getting close. 600. Oh, now we're too far. Now we have more products that can turn into reactants than reactants can turn into products. So let's try 650. That's pretty darn close. All right. This ratio right here is the ratio of products to reactants that have enough energy to react. I want this ratio to be 1 to be at equilibrium. If this ratio is 1, the rate of the forward reaction is equal to the rate of the reverse. That has to be true for equilibrium.
Yes.
Right? But what is the value of K?
2.07.
2.07, because at this point where we have the same number of products that can turn to reactants as we have reactants that can turn to products, the number of products compared to reactants, 1350 over 650, is 2.07. Okay, so for this setup, we have an equilibrium constant of 2.07. Cool?
Yes.
All right, so now you got a nice, good Maxwell-Boltzmannian understanding of how equilibrium works.
Does equilibrium apply when you like burn something?
Yes.
It does.
Yes.
What if
Well,
it burns
let's
completely?
let's read back to 6A. Any bond or intermolecular attraction that can be formed can be broken. Yes, equilibrium applies when you're burning stuff.
Like how we like.
Now, burning stuff is exothermic. So in general, exothermic reactions, you're going to tend to have more products than reactants, and probably way more than a 2-to-1 ratio. But there is still a possibility that, you know, some things stay as reactants, or that your products get converted back into reactants. Okay. Now, what's going to happen? Everybody agree we're at equilibrium?
Is it because the two shaded lines are lined up?
It's because the area of this shaded curve,
Oh, okay,
So
I see that.
the integral of this part of the red curve, is equal to the integral of this part of the blue curve, and actually up here is where I'm actually taking the area under those two shaded parts to see how many particles can
Is
be.
that what the product to reactant ratio that have enough energy to react? Is that the areas under the?
No, this is the ratio of the areas under the curve. I want that ratio to be 1. That means the same number of
But it
products
looks like the blue one's a lot bigger than the other one.
the total height of the blue one has to be bigger
No, I mean like
because
the area looks a lot bigger because they're on
Well,
the
you're
same.
wrong.
They're lined up together.
No, they're not.
You're wrong.
No, they're not.
you're on. You cannot do visual integrals. You want to
Wait,
come up
wait,
here and
Mr.
chop this
Boy.
thing up
Yeah.
with the scissors?
Mr. Boy. Mr. Boy. Mr. Boy. Point to the cutout line again.
Okay, let me actually.
Point,
There's
no,
a little
no,
bit
just,
of an issue
you can't
with
see
the.
the shading. You can't see the shading.
Yeah, the
That's
shading
only
is a little
problem.
weird here because they're.
If he sees the shading, he'll get it. You just can't see it. Also, sorry, I copied the
Oh,
wrong
okay,
name.
yeah, that makes.
Okay.
Okay,
So
yeah.
this is the area of reactants that have enough energy to turn into products.
That's what she was talking about earlier with the transparency.
Yeah. All right. Okay.
Should've
Now we
been
agree they're
said.
pretty
I
much the
thought if
same.
they were lined up, and the other one was like that.
Yeah. There's a little bit of an issue with the transparency thing, but I wanted you to be able to see when one, you know, if it wasn't transparent, you wouldn't be able to see the pink one at all. So, yeah, still better than me trying to draw these all by hand.
Doing simulation.
Okay. The big payoff. The big payoff. What's going to happen when I change the temperature?
They're both gonna extend.
We can extend.
Like they'll have a bigger distribution of like particles, and like the tip of the like parabola thing is going to shift to the right.
Okay, so we know we're going to spread out the distribution of speeds, but in general, the speeds are going to get faster, right? Temperature is a measure of kinetic energy, so when the temperature goes up, the kinetic energy should go up. All right? 120, boom. You see that one shift? 120, boom. I'll go back. Cool. Okay, now, the question is what happened?
That ratio got messed up.
Now the ratio is not 0.99, whatever it was before. Why not? Let's think of it. Who had a harder time reacting to begin with?
Reverse.
The reverse, right? It was harder for our products to turn back to reactants than it was for our reactants to turn into products. So when I increase the temperature, who's going to feel a bigger increase in the number of particles that can react? The products, right? Look at how much bigger, as a fraction of the total curve, the blue is right here. Right now, it's well over half of the curve can react, right? If I go back, before we had less than half of the particles that were able to react. On the red one, right now we've got about 2/3 that can react. Here maybe we've got 80% that can react, but it's not as big of a change for the reactants. We already had a lot of reactants that could change anyway. We're increasing that by a little bit, but not as big of an effect as it has on the products. Okay? So we're not at equilibrium anymore. We've got way too many products that can turn into reactants, so I'm going to have to get my products to go down, right?
Which
Ooh, pretty
side,
close.
50, no, 60.
which side feels the impact more when you have?
Hold on, girl. So let me finish this thought. I think I know what you're about to ask, and I don't know if there yet. Okay, so now with 850 and 1150, now we're about back to equal rates of forward and reverse, right? 0.993, close enough. Okay, but look what happened.
The K change.
The K actually changed.
Oh no.
When we change the temperature, K changes. Not Q, K.
K goes down.
So now, if K changed, then Q can't equal K, right? With the original number of particles that we had in there, right when I changed the temperature, that is not representing an equilibrium ratio anymore. Not because Q changed, but because K changed. Okay? So now, the system has to shift to get to the new K value. All right? Here's another way I like to think about it. Let's go to this simulation. Okay, let me go, what was it? 115,
115.
ooh, stop. 115 and 185 was equilibrium?
Yeah.
Yes.
Okay, so if we think about it, let's say this represented the amounts, well, we said it was 1.61 at whatever this temperature is, right? We saw 2 in the simulation before, okay? So, do a little dashed line here at 1. So we had a 1.61 K value at some temperature. When I increase the temperature, this is temperature versus equilibrium constant. If I increase the temperature, do you think the equilibrium constant is going to increase or decrease?
Didn't it decrease?
It decreased in the simulation, right? We were at 2.07, increasing the temperature, now the K went down. Which should make sense, because if I make the temperature infinite, then all particles can turn from reactants to products, and all particles can turn from products back to reactants. So the K value would be 1. So when we increase the temperature, K approaches 1. If I decrease the temperature, what's going to happen?
It's gonna go up.
K is going to go up. When I decrease the temperature, it's going to be harder for these products to get out,
Oh.
and so we're going to end up sort of accumulating particles in this product side.
Oh, that's
Right?
what the ruler stands for. Okay.
Or if you think about it from this perspective, if we went down to 30 Kelvin, okay, now we're clearly not at equilibrium here. We might have to get to something like, well, still not good enough. Something like this, right? Really decreasing the temperature, now I have to have way more products than reactants for these to be equal, right? Because as I'm making the temperature lower, it's even harder and harder for a product to actually work its way back, right? We're really shrinking down this fraction of products that can turn back into reactants. That means we're going to have to increase the overall size of the products pile until we have enough products that can turn back into reactants to balance the reactants that can turn to products.
So whichever side of the reaction that feels, whichever side of the reaction that's like harder for the reaction to happen, it feels the impact of temperature changes more.
Sure, you can think about it that way.
Okay.
Okay. Now, this curve that I just drew only applies for exothermic reactions,
Oh, no.
or really reactions that have a K greater than 1. If the reaction has a K less than 1, what's going to happen?
The opposite.
Just the opposite. Okay. As we increase the temperature, K is going to increase. So if I increase an endothermic reaction, if I increase the temperature of an endothermic reaction, K increases. Q stays the same at the beginning, right? So then if Q stayed the same but K got bigger, Q is less than K. How does this system shift when Q is less than K? To the right. So increasing the temperature of an endothermic reaction shifts to the right. Decreasing the temperature of an endothermic reaction is going to decrease the value of K. When Q is greater than K, we shift back to the left. Okay? Now that one is really, really hard to understand, so you might have to go and watch this boring YouTube video. Karina, are the numbers still counting up on that thing? Tell me they are.
Yeah.
Yes! It's a good thing I cleared all those stupid Logan videos off there.
You say
Really
the same
hard.
thing every single time you record.
Well, I only got so many jokes. What do you think? I'm like joke factory over here? Chemistry teacher. Alright, now, I hesitate to do a bad teacher thing and teach you a crappy shortcut.
Nah.
But because this is, I admit this is very confusing. Okay, I'm going to give you a way to very easily think about which way it will shift so that you know what the right answer is, so you're not confusing yourself thinking about Maxwell distributions and getting the wrong answer. So I'm going to show you exactly how to predict for temperature every time. It's not something I want you to write on the test, because if you write on the test, you will not get points. But if you're trying to think of, okay, it's endothermic, which way does it shift if I increase the temperature? Well, a really bad way of thinking about it is that in an exothermic reaction, is heat released or absorbed? Released. So if we were to put heat, if we were foolish enough to think that heat is a substance, would we put it on the product side or the reactants?
The product.
Products, right? Whereas if it's endothermic, we could say that heat is like a reactant. Okay? If you do that, then you just have to think about it like adding something or removing something. If it's exothermic and I increase the temperature, what am I doing?
Increasing the product.
I'm adding products. If I add products, the system shifts to the left. Right?
Yes.
Now, we said the real reason it shifts to the left is not because heat is a thing, but because increasing the temperature of an exothermic reaction decreases the K value. If your Q is bigger than your new K value, we're going to have to shift to the left. Okay? Decreasing the temperature is like taking away heat.
So it's good.
Taking away heat, we have to shift to the right. That's like removing products. We're going to shift to the right. Okay, I only want you to do this sort of reasoning so that you know which way it shifts. After you know which way it shifts, you have to think about, okay, what does that mean about K? We know K is changing when we change the temperature. Okay, so if it shifts left, well, let's see, what has to be true about Q and K if we're shifting to the left? Q has to be bigger than K, right? Too many products, not enough reactants, okay? So if you think about it, you could say to yourself, well, okay, if K was 1 originally, then Q was also 1 at equilibrium, right? If we shifted to the left, that means K must have gone down, right? So then even if Q was 1, if my new K was 0.9, Q is greater than K, we have to shift to the left. Okay? Again, I want you to explain it in terms of the change in K. Not saying that heat is a thing that you're adding or something like that. That's totally bogus. Alright? Now, the opposite is true for endothermic. If I increase the temperature for endothermic, that's like adding reactants. If we add reactants to a system at equilibrium, we shift to the right. Why does it really shift to the right?
Because Q is less than your new K.
My K is increasing, so Q is now less than the new K. System has to shift to the right to reestablish equilibrium. Okay? So this is your crutch,
This makes so much
but you
more
can't
sense.
just
than the
walk
other
on
things
crutches.
you
You
said.
still have to use your legs.
This makes so much
Fuck
more
that.
sense.
As it should.
This is not.
Cool? All right, Le Chatelier, we're done.
Yes.
We did it all. It was only an hour-long YouTube video.
5 minutes.
Hour and 5? Cool.
Just slap ads.
I think this one's going for like 2 million views.
Just slap ads.
Pretty sure.
This one's gonna have 12, and I'll probably
Profit.